Thank you everybody here for joining us. So today's topic, thermal management with CST Studio Suite. The idea is that I give a very brief general overview at the beginning, and then I would like to demonstrate how we can do such a coupling ending in a thermal simulation in CST. And I figured maybe at the end I say a few words also about some special cases like PCBs, or maybe not so special. Okay, so let's start with the general overview. As you can see already, we do have some options when it comes to coupling. And specifically when it comes to thermal management, we can go from Microwave Studio, from PCB Studio, from EM Studio, or from Particle Studio. Export losses, so be they in the materials, be they on components when coming from PCB Studio, or even losses from particles crashing into something from Particle Studio. We can take these losses, put them into our thermal solvers, and depending on the simulation type, give back the temperature also again to where the losses originate from. So there's a couple of different types of workflows that are possible. The most common one, I would say, is actually unidirectional. That is, we generate a loss, we take this loss, pack it into the thermal solver, and get our temperature distribution. Another option would be to go bidirectional. That is, we create our loss, pack it into a thermal simulation, push back the temperature to our EM simulation, and here we would then update material properties. So of course we do need to have temperature-dependent materials present in this case. Update material properties in this way, update losses again, go back into thermal until we are converged there. And you might have noticed already we have several thermal solvers here that are depicted as icons. The CHT solver, THS, THT. So why do we have different thermal solvers? Well, THS and THT, that's steady state and transient. They are both classic solvers. That means we don't have any explicit simulation of convection or phase-to-phase radiation. Whereas the CHT solver can be used as a steady state solver, can also be used as a transient solver. And here we do have explicit simulation of convection and phase-to-phase radiation. So just to get an impression for what that means, we can maybe take a quick look at the setup here. So this is our CHT solver. What do we specify here, for example? We have set a gravity. Okay, so we are doing convection explicitly, so we need to know in which direction gravity points, so we know where the hot air, in this case hot air, in which direction it will rise. We could also specify a radiation temperature, because we have surface-to-surface radiation also, and this will also be used in the simulation. So if we take a look at the temperature, this corresponds to our to what we can see typically. When we look around, we see a heat source, the air above is flimmering. Why? Because the hot air is rising upwards. And this heat plume is nicely developed and can be seen here as a simulation result. Now, if we go to the classic solver, the thermal steady state classic solver, it looks a bit differently here. So if we take a look at the solver settings, there's no gravity here. We set thermal surface properties in this case. So here we explicitly specify a convective heat transfer coefficient. And if we take a look at the temperature, this does not at all look like what we had for the CHT solver. There's no heat plume. Why? Well, if we're not simulating convection explicitly, we don't have hot air rising up. We just have heat going out through the properties of the air, and our actual contribution from convection is simply handled by the boundary conditions that we set with these thermal surface properties here. And that is why the overall picture might look very different. But actually, if we zoom in and take a closer look at the temperatures that we have in the solid itself, okay, here it still looks a bit different. But if we zoom in like this, we can see it's pretty much the same temperature. Of course, this depends a bit. So in this case, I made sure to set the same convection coefficients in the classic that were beforehand determined by the CHT solver. And if we had used radiation, it might have also made a difference. But I'm just saying that the takeaway here is simply we can use THS solver very effectively. It's a lot faster. We have adaptive meshing. It's easier with the meshing overall. We get the same kind of result here. We can also use it for a quick look to see if things make sense, if we are below certain temperatures. So we don't always need to use the CHT solver, but nevertheless, this will actually, the CHT solver will be the focus that we, or will be what we look at in the demo in a moment. So this is the solver that of which we will see results there. Yeah, we can relatively easily set up EM thermal coupled simulation. So there's a corresponding entry here, which we will see in a moment in the schematic, or it can also come from 3D, in fact. And yeah, we will take a look at simulation projects of this type in a moment. What we can also do to some degree is couple to Abacus. So there are different options available for this. So we can go with the, okay, I mean, both are actually co-simulations, but I just call this one co-simulation. This one is GUI driven on the CST side. It works with the low frequency solvers LF and LT, and it's a bidirectional exchange or unidirectional exchange of losses and temperature. The sequential workflows are a bit more general with regard to the solvers that can be used. So basically anything that uses TEDmesh. And by now also, in fact, surface losses from the T-fit solver. We can import losses or transfer losses from a CST simulation to an Abacus simulation. And we can also do a concentrated force. So the overall force on an object or group of touching objects, and transmit that to Abacus, and this will actually be extended further on in the year to also include force distributions when coming from the low frequency time domain solver or the M-static solver. There's also a few macros available that can forge connections to Abacus, create a model import for Abacus, and import temperature distributions from Abacus to the CST T-solver. And with that, I would like to actually go ahead and take a look at our model here. So in this case, we're looking at a diplexer. We have an F-solver simulation set up here. Now, how would I go about this if I wanted to set up a thermal simulation? Well, very easy. I'll switch over to the schematic, go here to simulation project, EM thermal coupling, and at the moment, I'll only set up something unidirectional. So you can see already I can create a simulation project here. So I'll just do high frequency domain just as the main project. And then I'm already set here in the project type to thermal and mechanics. And we'll select the conjugated heat transfer solver, click OK. And the setup wizard will automatically set up both monitors on the EM in the EM simulation project and loss import corresponding to these monitors on the thermal side. So let's see. I want to use loss frequency. So the parameters are already defined down here. And oops, loss scaling factor. Okay. And we can see the simulation projects have been set up. All right, so what has the wizard already done if I look here? So I do have these field monitors here now. loss, E field, and H field. In this case, since I'm using the F solver, I would only need the loss monitor, but doesn't hurt to have these available, of course. And also in the post-processing templates, I have already gotten this thermal loss calculation template, which will make sure that the thermal losses that are generated here will be put into a format that the thermal solver can easily read in. So in order to use this for simulation, I should, in this case, take a look at the background, and PEC is maybe not what I want to do, so I go for lossy metal, and I will just copy properties from a material. In this case, I don't have the material of the filter already set up, so I can just load that from the material library, and I'm looking for aluminum. So there we go. Okay. So I have a lossy metal background now, which means I will have losses on that background, and I will simply add a little bit of a distance everywhere so that I also have background everywhere. And that